How's it going today, guys? A little different location for this one. So we're going to continue on with three-phase alternators. We're going to go through a little bit of math calculations. So with the three-phase alternators and from the labs that you guys had, the last lab specifically, you ended up looking at a three-phase alternator when it's parallel to another one and what all the criteria were for making that happen. Just a reminder for that we needed the same voltage between the two machines. We needed same frequency between the two. We needed the same phase rotation, and remember, phase rotation didn't necessarily mean the direction of the alternator, which way it was spinning, or the prime mover, because you could change the output of that three-phase alternator by changing line 1 to line 2 at the terminal, and then that they had the same in-phase opposition, that they are reaching their peaks at the exact same time. And then once all four of those were done, then you end up closing that synchronizing switch, and then you transfer the load from the one that has the current draw at the time, or is supplying the load, and then so you lower the power of the one that has the load, and you increase the power of the one that is receiving the load. So other than that, there's not too much, but what I would like you to do is read through the section in Delmar's on synchronous alternators, please. It will be very beneficial, and there's also a portion in there on the synchroscope, and the synchroscope is what ends up being used instead of the 3-light method that we used last week. So please go through and read that. I am thinking about maybe putting some quiz questions online for three-phase alternators, possibly tomorrow, but I'll also talk to that when we go through the next video, or I'll post it as I post the link for the video tomorrow. But yeah, so the next thing I want to get into is some of the math related to three-phase alternators, and there's a few formulas I want to go through. First formula is percent efficiency. So percent efficiency is equal to power out over power in multiplied by 100, and that's how you get percentage. So that's the first formula. I'll try to make sure I stand clear. Next formula we're going to be looking at is our power factor, and that's going to be our true power over our apparent power, and obviously that would become a decimal, but if you multiply it by 100, you can get it as a percentage. And then also want to look at our frequency formula. So frequency is equal to our number of pole pairs times the speed divided by 120. Okay, so 120, this is a constant. N is our speed in RPMs, and then we have our pole pairs. And just remember with this too, when I say pole pairs, obviously that means a pair, meaning 2 inside an alternator, but if I ever write down a value for poles inside an alternator, let's say I give an answer of, oh, there are 10 poles in the alternator, I'm referring to pole pairs. I'm not asking you to do any math. I'm not asking you to take that value and divide it by 2 in order to get 5 pole pairs. If you do see it in a question, it just means that that is the value you're going to plug into the formula. Okay, and obviously frequency is measured in Okay? All right, and then there will be a little bit later on, but let's start just with this. All right, so we're going to start with frequency actually. So frequency, I'm going to say that I have 4 pole pairs, and I've got a speed of 1800 RPM, and I want to find out what the frequency of the alternator is at this point. So 4 times 1800 divided by 120, so that's 7200 divided by 120, and you'll find that this has a frequency of 60 hertz. So all the alternators in the lab that we use, because we have a set speed that we use for our prime movers of being 1800, and the alternator has 4 poles. So those synchronous alternators, whether alternator or motor, obviously being the same, they have 4 pole pairs. The output is going to be 60 hertz, and as you know, that's what we use in North America. One interesting thing, and we had talked about, remember with our EG is equal to K phi N, is that as speed goes up, right, we end up generating more voltage. We also see that as speed changes, so because it's on the top, it's the numerator in the formula, if that value goes up, because it's multiplied by 4, my frequency is going to go up. If the speed goes down, then my frequency is also going to go down. So it's very much, frequency is tied or will be dependent on what the speed of the prime mover is. Especially if you go to install a generator, let's say it's on a house, it could be a single phase generator. You need to make sure that the speed of that the prime mover on that generator is going at rated speed, otherwise you won't get the rated frequency of it. And if that frequency is off a couple percent either way, or a few percent either way, it can be harmful to the equipment that you're running. So very important that speed is maintained the same. An interesting thing to remember, we were talking about similar frequency outputs. If I started doing, let's say I have 2 pole pairs, and we have 3600 RPM, and I want to know what the frequency of that is. If we plug that into the formula, we have 2 times 3600 divided by 120. So 2 times 3600, 7200 divided by 120. That also equals a frequency of 60 hertz. Sometimes individuals think that the speed is a determining factor when synchronizing both alternators. That the speed always has to be the same. Well, if we look at this, we've got 60 hertz as our output on a 3600 RPM alternator, and we also have an output of 60 hertz when we have an 1800 RPM alternator. So speed is not a determining factor. It's obviously the relationship between the RPMs and also the poles that gives us the frequency that we have. So frequency was more that determining factor when paralleling, so it was voltage, we had a frequency, and then the other two were the in-phase opposition and the same phase rotation. Okay, so that's fairly straightforward. Okay, next, I'm going to look at efficiency of our alternator. So we've got, it's going to be our alternator, and these are my line conductors, line 1, line 2, line 3, and anytime we talk about alternators, there's terms that will be looked at or discussed where we talk about supplying the load. So an alternator is if it's supplying the load or it's delivering to delivering to the load. It's talking about these conductors here. These would be supplying the load. So this obviously would be being sent to potentially another motor or to lights. Then we have our shaft of our alternator. And then the shaft of that alternator needs to be spun by something. So a prime mover, could be a DC motor like we use in the lab. It could be a turbine, could be a windmill, could be a little hamster on a hamster wheel running around. But something has to spin that shaft. Our power in is going to be seen on the shaft. So what's being delivered to the shaft of the alternator from our prime mover. And we could even draw another motor at the side, a little DC motor. And this one being our three-phase alternator. So power in is what's being delivered on the shaft. Our power out is going to be seen at this point on the output of the alternator being delivered to the load. One other thing, our power input is never going to have a KVA value. There's no inductive properties that can be applied to the shaft because it's not part of the overall wiring. There's only a magnetic field that's between the two of these, so it's the power delivered from the motor onto the alternator is going to be your power in. However, my power output, and remember power, when it refers in this situation, the power output is going to be a true power. So true power is the output value, so that would negate any power factor that's in the circuit, so any inductive or capacitive losses. And our power in is also going to be a true power value. So that would be measured in watts or horsepower, and you can bounce back and forth between the two. And remember that 1 horsepower is equal to 746 watts for when you're going between the two. However, on these line conductors, we can also look at a power factor, or would have a power factor if there was a inductive or capacitive load added onto this. So you would also see a KVA value, potentially, or a volt amp value over on this side. So our power in is going to be bringing, or what's spinning the shaft of that alternator, and then our power out is going to be the line conductors coming out of the alternator. And so we see our power out over here, we see power factor over here, and inevitably we are going to see a kVA value. All right, I'll give you some examples now that we can go through. I won't do a whole lot now. In Lab Class Friday, I'm going to hand out some more sheets that pertain to some questions for an alternator test. So we are going to look at the question in mind. We're going to have our kVA value, and the output of our alternator is going to be 12 kVA, and we're going to have a power factor of 95%, and we're going to have an efficiency of 89%. So nicest thing to do with this, or best thing to do, is to lay things out so you know exactly where they're going to be going. So obviously our power in is going to be here. Our power output is on this side, and then we also have our kVA. The efficiency of our alternator is going to be obviously due to the losses through our alternator. So there's 89% efficiency. So there's no way of us being able to increase power from this side to this side. The value always has to be smaller. So always remember when you're doing these calculations, if you lay them out like this, your power in on the left-hand side is always going to be bigger than what your power output is. So if you put something into your calculator and it doesn't seem, if you accidentally multiplied instead of divided, if you lay it out like this and know that the left-hand side is always going to be the larger value, the right-hand side is going to be the smaller value, it's going to help just focus your thoughts in your work and help you get the right answer at the end of the day. And then our power factor is going to be seen over here, 95% power factor. And let's actually, I think I can get further over. Let's do this as our kVA this way. Okay. So our kVA, we have 12 kVA, and we're looking for our power output from that. So when you're calculating these out, my power factor is equal to our true power over our apparent power. So our true power is going to go on the bottom. We have 12 kVA, and our power factor is 95%, or as a decimal is 0.95. And we want to get true power by itself. So how do we do that? Well, to get true power by itself, we have to multiply by 12 kVA on each side. So multiply by 12 kVA. And that gets our true power by itself. And remember, true power is always going to be a smaller value than what our apparent power is going to be. So if I plug this in, and we end up doing (12 kVA times 0.95), we get 11.4 kVA, or sorry, kilowatts. We have 11.4 kilowatts is our true power. So remember to keep that as true power. one thing, and it doesn't matter how you do this, you can take your 11.4 kilowatts and transfer it over to a power in the way it is. Or if you don't like working with larger numbers, you can change your 11.4 kilowatts into horsepower first and then transfer it over. Either one, it all depends on what you're being asked for. I'm going to just bang everything out so that we end up getting a wattage value at the end and a horsepower value at the end, just so you can see. So now I've calculated out what my output power is. So our output power is 11.4 kilowatts. And now we want to calculate what our power in is. And remember, it had to be a larger number. So we're now looking at efficiency. So percent efficiency is equal to power out over power in. So our power out, we know, is 11.4 kilowatts. And our efficiency is 89% or 0.89. And we want to get power in by itself. And one neat little trick, if you have a value here and you had a value here, rather than cross multiplying the power out or cross multiplying power in or whatever, flipping everything around, trying to redo everything, the easiest thing to do is all you have to do is just flip those two, okay? Just flip them like that. If you end up doing that, you get power in is equal to 11.4 kilowatts over 0.89. So that's the easy way of rearranging them. Otherwise, you would have to multiply power in on this side, multiply power in on this side, right? Which would then erase all that. And then you would have to divide out 0.89 and then divide out 0.89 to rearrange it. So nice, quick and dirty way to do it is just flip the values and you can start doing the math. So now I have 11.4 kilowatts and I'm going to divide that by 0.89 and I get a value of 12.81. We'll round up 12.81. So 12.81 kilowatts as our power in. So that would go over here. And notice when we went to the left, the value got larger. When we went to the right, the value got smaller. So the smallest value in here should be what your power output is, because there's losses through your alternator, whether they're from mechanical losses, heat losses as you end up going through, I squared R losses is going to end up being smaller, and then obviously depending on what's connected to it, if you've got an inductive or capacitive load, your output kVA will be larger than that value. So we've got 11.81, and then the last thing I want to do is just convert that to a horsepower. If I divide that by 746, I get a little nicer number. Divide that by 746, and we get 15.28 horsepower. So these are all things that I'd end up asking on a question in the next video tomorrow. I'm going to be going through how to answer word problems with these in them. So in answering word problems with these in them, I just give you a question with all the information. You need to learn to pull that out and end up using that. But 15.28 is the horsepower from that. I could also, in the same question, have all this information plus also the frequency stuff to ask what the speed of that alternator would end up being. Okay, so that one's done. What I want to do next is go from the other way. And what are we at time-wise here? 25 minutes. So I'm not going to make this one overly long just because I'm doing a fair bit here. I'm going to give you one more question going the other direction. So go from left to right. And then I'm going to write a question on the board that you guys can go through in your leisure time. Because I know this is something you look forward to doing every evening. So now we are going to start out with a power in is going to be, let's do 10 horsepower. We've got an efficiency of 82% and a power factor of, let's do 90%. And I want to know what my kVA output is. So kVA output is what the question is. Okay, so there's a lot to unpack here with this one, but we know that 10 or our power in is 10 horsepower, so that's over here. And our power out is going to be on this side, and we don't know what that is. So you can leave it as 10 horsepower, or you can convert it first. I'm just going to convert it first because I think the majority of you will do that as well. So multiply by 746. If I do 10 times 746, I get an answer of 7,000, or so 7.46 kilowatts as what our input is. We have an efficiency of our alternator of 82%. So from going from this side to this side, the value is going to drop by 82%. It's going, so it'll be 82% smaller. If I put that into my efficiency formula, so efficiency is equal to power out over power in. We have a power in of 7.46 kilowatts. And we have an efficiency, as we said, of 82%, which is also 0.82. And I want to multiply 0.46 kilowatts on this side to get it over to there. 7.46 kilowatts multiplied by 7.46 kilowatts. I'm sorry for being in the way. So 7.46 kilowatts times 0.82. And this will give me what my power output is. And some people can even see without putting into the formula that, oh, to get the value smaller, I need to multiply it. So we have 7.46 kilowatts times 0.82. So we get 6.117. So I'll leave the 7 in there just to make it a little more accurate. So our power out is equal to 6.11. I think I said 7. Okay, so that value ends up going here of 6.117. And if you look at these two numbers, as we went from the left to the right, the value got smaller. So we know we've done at least something likely right because it got smaller. And now what we want is we want to figure out what our kVA is from our power factor. So power factor is equal to true power over, and that's a kilowatt value, sorry, 6.117 kilowatts, times kVA, or divided by, sorry, our apparent power. So if we do that, we get 0.9 for the power factor. We get our true power value of 6.117 kilowatts. And we want to get apparent power over here. Remember what I said before, if we want to move that, we just flip it. So apparent power is equal to 6.117 kilowatts divided by 0.9. And the value should be getting larger because we have a reactive value in there. Divided by 0.9. So we have 6.797. So apparent power is equal to 6.797 kVA. So that would be the answer for that question. All right, so we had losses through our alternator. Your power, output power would be smaller. Then we look at the power factor and we get a kVA of 6.797. Okay, I am going to put just a couple values, a little bit on the board. I'm going to do a question that ends up having a frequency calculation on it and also efficiency. So I'm going to do a couple different variations of this. So we've got a 20 kVA alternator. First scenario, this will let you do a couple little practices with it. We are going to have 81% efficiency and 97% power factor. And then we're also going to do a 75% efficiency, and let's do 85% power factor, all with the same alternator. So just see how those values compare. And then I'm going to give you, we have a 15 horsepower alternator, or sorry, let's do a power in, sorry, supplied from the prime mover of 15 horsepower, and we're going to do 86% efficient and 90% power factor, and we're going to do 93% efficient and 95% power factor. And let's do actually, this alternator has or runs at a speed of 500 RPM, and it currently has an output of 41.667 hertz. Okay. So from this, I want you to tell me number of poles, so pole pairs, what that is. And then on top of that, I want to know how much faster that alternator needs to go to get an output of 60 hertz. Okay, so doing this will let you know how many poles there are, and then I want to know what you would need to do, or how much faster you need to go to get that to 60 hertz. So last part, so speed increase needed. I think I'm not on board. So speed increase needed to reach 60 hertz. So 2-pointer. I think you guys think just a little bit on that one. And if you take some time to do that, that should fill in the rest of the time for class, and should give you a little practice. Okay? All right. Have a good one, guys. Bye.